Welcome to iTTV for Form 5 Physics. The title of this lesson, Damping and Resonance in Waves. In this lesson, we want to have a look at two unique phenomena of waves which are called damping and resonance. In damping, what we're going to notice is that as a wave is traveling, its amplitude will decrease in time until finally the amplitude will reach a zero value. This means that energy is being lost from the wave because the amplitude is decreasing. This is called damping. Then we want to have a look at resonance. In resonance, a wave or a vibration is going to start vibrating at a higher amplitude. In fact, the amplitude sometimes becomes twice as much as the original amplitude. So, when that happens, we say resonance is occurring. Let's have a look at two of these phenomena and what are the factors that affect both of them. Periodic motion. Any motion that repeats itself in equal intervals of time is called periodic motion. If a particle in periodic motion moves back and forth over the same path, we call the motion oscillatory or vibratory. So, this means that if you constantly repeat your action, such as waving your hand, we'll say that this motion is oscillatory or vibratory. Damping in an oscillating system. A little boy is swinging on the swing. Particles in periodic motion move back and forth over the same path. The motion is oscillatory or vibratory. So when the little boy is swinging on the swing, we say that we have oscillation. Many of these oscillating bodies do not move back and forth between precisely fixed limits because frictional forces dissipate the energy of motion. Thus, a pendulum that is swinging will stop swinging after some time. So what we are saying is, because of external or internal frictional forces, what's going to happen is that this oscillation is going to diminish and eventually come to a stop, meaning that your amplitude is also going to decrease. So if you have a pendulum, let's draw this up on the board. If you have a pendulum that starts swinging from point A all the way to point B, so it's going from here to here and then back again. After some time, what's going to happen is this distance is going to start to diminish. You're going to get that it's only going to swing so much. Now, the reason for this decrease in swing is because energy is being lost to the surrounding. So we are losing energy. Energy is lost, and the energy is lost or dissipated due to frictional forces that are working both externally, example between the string of the pendulum and the material you're tying the string to, and internally because of forces of attraction and repulsion inside at a molecular level. So finally what you're going to get is the pendulum is hardly going to swing at all until finally the pendulum comes to a stop. So you get a sequence of a large amplitude, a smaller amplitude, and even smaller amplitude till finally the amplitude becomes zero. So as you can see, a pendulum which is swinging, ultimately its amplitude decreases until it slowly but surely comes to a stop. An oscillation system that loses its kinetic energy and potential energy will cause the amplitude to decrease. There are two types of damping. External damping. energy loss due to air friction. Internal damping, energy loss due to attraction and repulsion between molecules in the oscillation system. A graphical presentation. Emphasis on the fact that the amplitude decreases exponentially and the wavelength remains the same. So if you look at the two graphs, you can clearly see the amplitude is decreasing with time, but the wavelength is unchanged. So in damping, please remember this, the wavelength is not going to be affected. Only the amplitude is decreasing. So things like the wavelength, frequency, and the speed of the wave or the oscillation is unchanged. Only the amplitude decreases. Activity: resonance in a Barton's pendulum. Aim: to observe resonance in Barton's pendulum. Apparatus: 5 pendulum bob, strings, 2 retort stands and 2 G clamps. Introduction. The period of oscillation of a simple pendulum depends on the length of the pendulum. Since frequency is the reciprocal of the period of oscillation, we can calculate the frequency of the pendulum. So what we are saying here is frequency, which we know from our last lesson, equals 1 over t, t being the period. So if we know the period, we can clearly calculate the frequency of oscillation of the pendulums. The diagram shows the setup for Barton's pendulum. There are many horizontal pendulums tied to a horizontal string. Each of these pendulums will be forced to oscillate dependent on the length of the pendulum. When the pendulums oscillate, damping of the pendulum will occur. So what we do is we make one of the pendulums oscillate. That oscillation will transfer itself through the string to all the other pendulums. So all the other pendulums will also start to oscillate. Now once oscillation begins, damping will follow. And eventually the other pendulums will start to slow down, or their amplitudes will decrease until they come to a stop again. Energy of oscillation will be lost because of the air resistance. The swing of the pendulums will stop after some time. There is a pair of pendulum, B and D, that are tied to strings of equal length. As frequency depends on the length, both pendulum of equal length will have the same frequency. These two pendulums will oscillate at the same frequency. When one of the pendulum, example B, stops to oscillate, its energy is transferred to the other pendulum D. Resonance occurs in oscillation of the pendulum D, and it will oscillate at a greater amplitude and a longer time. So the key here is, for resonance to occur, the forced vibration of one oscillating system upon another oscillating system, in this case the forced vibration of B upon D, is very important that their frequencies are the same. If the frequency of B is the same as the natural frequency of D, we get resonance, where D will start to oscillate at a greater amplitude. The amplitude will be at a maximum value. So let's have a look at this on the board. So if you imagine that we've got a string connected to 5 pendulum. So I've got the first pendulum here. This is the pendulum that I'm going to start with. Slightly different to the diagram you have in the slide. So this is pendulum A. So then I'm going to put here pendulum B, pendulum C, pendulum D, And finally, pendulum E, which is going to be the same length. Now, when I start swinging pendulum A, the vibrations of pendulum A are going to travel through the string, and it's going to start make pendulum B, C, and D vibrate. So all these three are going to start moving. But eventually they'll all come to a stop due to damping. But with E, because they have the same length, because the length are equal, they have the same frequency, which means to say that the frequency of A is equal to the natural frequency of E. So when this vibration reaches E, E will not just vibrate, but it will vibrate with maximum amplitude. This is resonance. And the key to resonance is to understand that the forced vibration, which is coming from A, so here we get our forced vibration. The forced vibration is equal to the natural frequency. Because the forced vibration of A is equal to the natural frequency here. When I say forced vibration, I mean the frequency of this forced vibration. So let's add that in here. Frequency. Okay, so the frequency of the forced vibration is equal to the natural frequency, and if this occurs, we get resonance. And when resonance occurs, your amplitude is at a maximum. So remember, the key here is the forced vibrations frequency is the same as the natural frequency, and then you get this resonance occurring. As this pendulum D slows down in its swing, pendulum B that is moving with the same natural frequency will oscillate again. How resonance occurs? In a damped oscillation, the amplitude becomes smaller with time. An external force is required to apply to the system to force it to oscillate again. The system is under forced oscillation. When the forced oscillation is equal to the natural frequency, resonance occurs. At resonance, the amplitude of oscillation will be maximum. Resonance. System oscillates with its natural frequency and maximum amplitude. It is subject to a driving force with same frequency. Application. Big pipes are fixed at the back of the hall. If these pipes vibrate, the sound will create resonance with the incident waves and make the sound vibrate at a greater amplitude, and thus it will become louder. In this picture, you see a bridge collapsing. This is a negative effect of resonance. The collapsed Tacoma Narrow Bridge in 1940 was due to resonance. The air or the wind blowing across the bridge had the same frequency as the natural frequency of the bridge. This caused the bridge to vibrate at maximum amplitude, which caused the bridge to collapse. Exercise. In the photograph, it shows the back of a music hall. There are many big, thick, cylindrical metal pipes installed at the back. When sound hits on the cylinder, the cylinders are set to oscillate at the same frequency. What is the reason that these metal cylinders are built in a big hall? We've just discussed this. Why do we put these metal cylinders at the back of music halls? What is it that we want to achieve? Have you written down the answer? Let's have a look. A. To protect the glass window at the back of the cylinders from cracking when loud music hit on it. B. To generate additional musical notes. C. To minimize reflection of sound from the back. D. To have resonance of sound so that the music produced is louder. So, which of these is the answer? Why do we have those metal pipes at the back? Have you made your selection? Let's have a look and see if you've got the right answer. D. To have resonance of sound so that the music produced is louder. Let's try another question. When a system is made to oscillate at a frequency equivalent to its natural frequency by an external force, this phenomenon is called A. Damping, B. Resonance, C. Modulation, D. Rectification. So remember, an external force with a frequency similar or the same as your natural frequency, what do we get? Have you written it out? Have you picked the answer? Let's check. The answer B. Resonance. Let's try another exercise. The diagram shows a graph of an oscillation system experiencing damping. Which of the following quantity does not change? Size of oscillation, period of oscillation, energy of oscillation, amplitude of oscillation. So what doesn't change? Have you made your choice? Let's have a look. The answer is period of oscillation. Remember, frequency, wavelength and speed are unchanged. The only thing that changes is the amplitude, and the amplitude is related to the energy in the system and also to the size of the oscillation, how much it's moving from point to point. Summary. Motion can be oscillatory or vibratory. Damping is because frictional forces dissipate the energy of motion. When a forced oscillation is equal to the natural frequency, resonance occurs. And then you need to know the applications. With the example of damping, we use damping in our cars in the shock absorbers. The idea of the shock absorbers are to dissipate energy as quickly as possible, so we reduce the bouncing of the car. Or this can also be applied to a motorcycle. In factories, we use damping on the machinery. What this is for is to reduce the sound produced by the machines, so that the floors basically are made in such a way that they will dissipate energy as fast as possible, so that the vibration of the machines, the amplitude, is diminished quickly and the sound inside the factory is reduced. With resonance, well, we use this in our musical instruments. The flute, the saxophone, the guitar, the piano, all of these use the idea of resonance so that the musical note being produced is louder. Another example of resonance is when an opera singer sings and he or she can cause a glass to vibrate at a maximum amplitude that will then cause the glass to shatter and break. All of these are examples of resonance. We even use resonance in the manufacture of plastic, where the resonance, because of maximum amplitude, will cause the plastic to heat up faster, and then we can join pieces of plastic together by resonance. So these are some applications of damping and resonance that you need to know, so that if you come up with a question or face a question in the examination, you'll understand and be able to go like, here I'm reducing the amplitude, this must be damping. Or here, I'm increasing the amplitude, this must be resonance. That's all the time we have for this lesson. Thank you for watching ITTV.